Hello, quantitative methods. Let's finish up our lecture on the normal curve, the normal distribution, I should say. So we're going to talk about two things: standardized scores, which are important, but what's more important is sampling distributions. Sampling distributions are what we're going to be dealing with when we get to inferential statistics, looking at what are some characteristics of these sampling distributions, and the wonderfulness that is the central limit theorem. This will be a fun lecture that you will review a few times if I were to make a prediction. Okay, standardized scores. And we've already encountered a standardized score. I just don't think I called it that. Standardized scores are scores that we convert in some way to have a specific mean and a specific standard deviation. Remember our discussion when we talked about frequency distributions about the difference between raw scores and transform scores? So raw scores are the data that we actually get, right? It's maybe the number of items you got correct on the test. It might be the number of points you have on a test of personality. But sometimes it's hard to interpret those scores because they're just for that specific test. So one thing that we might do to increase their interpretability is to change them to a standardized score that we're more familiar with, okay, that has a specific mean and a specific standard deviation. The example that we've talked about already are z-scores. Z-scores, we take any old distribution of data and we set it to have a mean of 0 and a standard deviation of 1. Here's a question. If we convert things to z-scores, does this mean that whatever distribution we're looking at is normally distributed? In fact, if we have a distribution of data that isn't normally distributed, if we create z-scores, does this mean that the z-scores now are normally distributed? And the answer is no. Emphatic no. All right. Z-scores we can use and we can interpret them from that table that I showed you. All right. What percentage of people scored above and below this score, right, and all the useful stuff, only if the distribution is normally distributed. All right, you can count z-scores for anything. That doesn't mean that the distribution is going to be normal. All right, but z-scores are just a standardized score that have a mean of 0 and a standard deviation of 1. All right, converting things to z-scores doesn't normalize the distribution. Right, to interpret them the way that we do, we have to infer that there is that the data are normally distributed. All right, now z-scores are fine and lovely, and you'll see them many times in psychology. But for a reason that I'll talk about next slide, people sometimes don't like them. All right, so what are some other examples? IQ is probably one of the most infamous examples here. Way back in the day with Binet, IQ meant someone's someone's mental age over their chronological age, but there are many problems with that calculation, so it was quickly abandoned. Nowadays, anytime you see an IQ score, it's just a standardized score, the same thing as a z-score, but you set things to have a mean of 100. All right, 100 is exactly average intelligence, and you set IQ scores to have a standard deviation of 15. All right. So that means that if you have an IQ of 130, you are 2 standard deviations above the mean. And if the data were normally distributed, because again, standardizing these scores doesn't force the data to be normally distributed, but if the data is normally distributed, then we could look at, well, your 2 standard deviations above the mean, we can go to a z-score of 2 and think about how many people are less intelligent than you or more intelligent than you. All right, that's how we could go about doing this. All right, so IQ scores, mean of 100, standard deviation of 15. Another example that you're likely to see, particularly in education. Not just in education, for psychological evaluations, sometimes you'll see T-scores as well. T-scores are standardized scores that have a mean of 50 and a standard deviation of 10. Okay, and sometimes people will like working with like IQ scores or T-scores better than z-scores, and again we'll talk about why that is the case, but I mean, you always talk about people who, oh, my IQ is blah 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 blah. I mean, what they're just talking about the standardized score. All right, and who knows what intelligence test they got that standardized score from. I mean, some intelligence tests on the internet, or they got it from, are quite dubious. And they artificially inflate what your score is to make you feel better and make you want to take the test again. Yeah, those are a little bit dubious, but IQ is just a standardized score for a measure of intelligence, hopefully. Okay, those are some examples. So why would we want to use standardized scores? Why do we want to use things like z-scores? Well, one thing is to convert things to a common metric. Imagine, if you would, that there are two tests with two different scoring systems, but they're supposedly measure something similar. All right, how about something like the SAT or ACT? Now, I know that everybody's going to get upset with me and say, oh, these tests measure a different thing. One measures aptitude and the other measures achievement, blah, 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 blah. They're pretty much measure the same dang thing. There's not much difference between the two of them. They are veiled intelligence tests, okay? We say that they're not intelligence tests at colleges, and they don't market themselves as such, but they're pretty strongly correlated with intelligence, and that's the reason why colleges use them. But they have different scoring metrics, right? So in the SAT, you can score in the thousands. I think the average is like 1,600, or I don't know what the average is right now. They change that test so frequently. And the ACT, it's on the order of like 30. The average score is like 30, 36, something like that. So how do you compare those scores? We did this in a problem earlier. But if you were a college, how do you end up? I mean, you accept people that have the SAT, you accept people that have the ACT. How do you make a comparison, especially if it's down to the wire? Who is going to get into college, this person or this person? One's taking the SAT, one's taking the ACT. You can use a z-score to put these on the same metric. All right. Again, you're making the assumption that everybody's normally distributed, but you can look at the data that way. Something that I did with my research, I'm interested in working memory capacity. So think of this as someone's like short-term memory ability. Working memory capacity encapsulates a few more things than short-term memory, but it's kind of similar in some ways. But we have multiple tests that we use to measure somebody's working memory capacity. Here we have math problems that subjects have to solve, and between each math problem they get a letter. And after a number of letters and math problems, then a recall screen appears, and they have to select the letters in the same order that they saw them in. And so that's just one example of this task. We've got a few others, but the total score is different. The variability on each of these tasks is different. How can I find someone's working memory capacity score? And I want to take all of these three tasks into consideration. Well, again, you know, it's a little bit difficult because the total number of items is different for these three tests. The variability is different. But what I can do is I can convert the scores on these three different tests to z-scores and take the average z-score of the three and get a composite working memory capacity score that way. So taking the average of the z-scores by converting them to a similar metric. All right, you see that quite frequently in psychology. How about different personality tests? Somebody takes the Myers-Briggs type indicator and has their measure of extroversion. Someone else takes the MMPI and has that measure of extroversion. Someone takes the NEO personality inventory, and there's that version of extroversion. Let's say that we're doing some kind of like huge combination study, or we're trying to see if extroversion is correlated with blah. But we've got extroversion measured in many different ways. Do we throw up our hands and say, can't do the study? No, one thing that we can do is for each of those metrics, which has different numbers of total scores, different variabilities, different standard deviations, we can convert them all to the same metric, z-score, and it doesn't have to be z-score, but it could be z-score, and correlate it with whatever it is that we're interested in, maybe the number of positions of leadership someone has. 1 second, let me mute myself. All right, sorry about that. And my volume still turned on my computer. All right, so other advantages for using standardized scores. Well, if the data are normally distributed, and again, the data have to be normally distributed. If we calculate a standardized score, it doesn't make the data normally distributed. We know the percentages of subjects that scored above and below certain scores, right? It increases the interpretability of our data, of our scores here. So that's one of the great reasons for converting things to z-scores. We can understand z-scores a lot easier than we would just the raw scores for a test, because again, we might not know the average of the test. We might not know the total amount of points of the test. Z-scores really increase the interpretability of looking at the data. So why don't we use Z-scores all the time? All right, Z-scores are easy. People like them. Why do we come up with things like IQ scores or T-scores? All right. In fact, many times when we are reporting things to the public, to the lay audience, we do not use Z-scores. In psychology, we love them. And in most scientific disciplines, we would use Z-scores, which is they're easy, and everybody has a good intuition about what's going on with a Z-score. Why do things like T-scores exist in education, and IQ scores exist for the general public? And in the military, one thing that they're fond of is stenines. Stenines are not exactly a standardized score, but they're similar in many ways. So there's all these different kinds of scores out there. Why don't we use those instead of Z-scores? Well, think about a Z-score. The mean is 0. Let's say that you come to see how little Johnny is doing in elementary school, and your teacher says, little Johnny's doing great. Here's his score, and it's a 0. And she tells you that little Johnny is doing average in the class, but you're freaking out because it's a 0, all right? And even worse, let's say that your kid is below average and whatever, and then all of a sudden your kid has a -1 score. Well, you're going to be flipping out and thinking the teacher's not doing their job if your kid's getting a negative score. And people are going to have a visceral reaction to seeing a negative number for something like intelligence or school ability or something like that. So psychologists have quickly learned, or educational professors quickly learned, one thing that you can do is to convert these Z-scores into some other metric that's going to make people feel a lot better. So the average for a test of intelligence is 100. It is theoretically impossible. Well, I don't want to say theoretically impossible. Practically, it's impossible to get an IQ of 0. It's not going to happen. That means that you have to be 7 or 8 standard deviations below the mean. Look at that normal distribution that we have and think about how many people are above and below 3 standard deviation units. All right, very, very few people. All right, think about if we're looking at like 8 standard deviations below the mean. All right, very, 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 very few people are going to be in that regard. In fact, we'd have to have a special intelligence test to test somebody at that low level of ability. Same thing with T-scores. All right, T-scores, the mean is 50. The standard deviation is 10. You would have to be 5 standard deviations below the mean for you to have a 0. So in that way, it kind of assures people that, you know, person's doing average, they have a 50. Even if they're doing lower, it looks a whole lot better. So for aesthetic reasons and for people not flipping out at you reasons, we convert things to T-scores, or we convert things to IQ scores, or any other standardized score. They don't just have to be T-scores or IQ scores. So, you know, to artificially inflate, think about the SAT, right? The SAT could start at 0, but it doesn't. And, you know, people always say, well, if you just write your name on the SAT, you pretty much have 300 or 400 points. It's not exactly true. It's just that if we are looking at, it's a standardized score, right? The average of the SAT, if we look at everybody that takes that SAT at that one period of time, is X, right? And the standard deviation is whatever, right? It's just very, very difficult for you to get all the way at the bottom. And even if you turn something in, if we're looking at things in terms of standard deviation units, it might be impossible to get like a 0 or something like that. All right, so just a little practical reasons why we do certain things. All right, so let's talk about how we find and calculate a standardized score. So the first thing, there's going to be 3 steps. First thing that we do is we need to find the Z-score. All right, we're going to find the Z-score. So we take the score, we subtract it from the mean, and we divide it by the standard deviation. Okay, that's how we calculate a Z-score. We're going to multiply that Z-score that we've calculated by whatever the new standard deviation is. If we want to convert things to an IQ score, the standard deviation of IQ is 15, so we multiply the Z-score by 15. If we're looking at a T-score, the standard deviation is 10, so we're going to use 10. If we use some standardized score that has a new standard deviation of 6, we use 6. All right. So we get that product. Okay, remember a product is the result of multiplication. And we're going to add to that product the new mean. Okay, whatever the new mean of the standardized score is going to be. For an IQ score, this is 100. For a T-score, this is 50. For something else, whatever you want the new mean to be, that's what you're going to add. I want you to think about the logic of calculating this standardized score. If we convert something to a z-score, we have a mean of 0 and we have a standard deviation of 1. If we're going to multiply the z-score by the new standard deviation, we're multiplying the new standard deviation by 1. Anything multiplied by 1 is itself. So the old standard deviation is 1 from the z-score. We're multiplying it by the new standard deviation. So guess what the new standard deviation is going to be? Since we're multiplying the new standard deviation by 1, boom, it's going to be the new standard deviation. All right. The mean of a z-score is 0. So we're going to add the new mean. 0 plus anything else is whatever that thing was, right? So if we take 0 and add it to the new mean is going to be whatever we wanted the new mean to be. I hope that made sense. We'll see this in action, so hopefully that'll make a little bit more sense to you. All right, so we got Blake, and Blake surfs the internet and decides to take a measure of intelligence. And he gets 15 out of 30 items correct. The mean for the test is a 21. The standard deviation is a 5. And we want to find Blake's IQ score. So again, the first thing that we want to do is we want to convert this to a z-score. Blake makes a 15. We want to subtract that by the mean of the test, which is 21. And we want to divide it by the standard deviation of the test, which is 5. All right. So step 1, we are going to take 15 minus 21, which is negative 6, divided by 5. We've got a z-score of negative 1.2. All right. So the average IQ score is a 100. We should see that Blake has less than a 100. All right, we're going to multiply this by the new standard deviation, the standard deviation that we want. And for an IQ score, that new standard deviation is 15. So we're going to multiply this by 15, and we're going to get negative 18. All right, negative 18. And then we're going to add this to the new mean. The new mean that we want to have is 100, because again, the average of IQ scores is always 100. So negative 18 plus 100 is going to give us 82. And so we're going to say that Blake has an IQ of 82. All right. So not too terribly difficult, just a few more steps above and beyond calculating the z-score. Let's do one more example here. So we have Laura, and she takes a personality test that measures agreeableness, and she scores a 50 on the test, and which higher scores indicate people that are more agreeable. The mean of the test is 30, and the standard deviation is 14. T-scores, which we're going to convert this to a T-score, have a mean of 50 and a standard deviation of 10. What's Laura's T-score? Well, first thing that we're going to do is we're going to calculate a z-score, so we're going to take 50 minus 30 and divide it by the standard deviation of the test, which is 14. So this is going to give us a z-score of 1.429. Now this makes sense. Laura's score is above the mean. We should have a positive z-score. We do, so everything checks out so far. We want to multiply this by the new standard deviation, the standard deviation of t-scores, which is 10. So we're going to multiply this number by 10, and we're going to get 14.29. And we're going to add this number to the new mean. All right, the mean for t-scores is 50, so we should get 64.29. So Laura has a t-score of 64.29. All right, so far so good. Think about if I wanted you to convert something back into a raw score, and I had you a standardized score. Think about the steps that you would do to try to figure that thing out, okay? But for the most part, your problems, especially in homework, will look like what we've just done. Okay, so now we get to probably one of the most important topics, well, the most important topic in this video, one of the most important topics in this normal distribution module as well, sampling distributions. All right, so we're going to be dealing with a lot of sampling distributions, so it's important that conceptually you understand what's going on with them. All right, so far when we look at distributions, the distributions are from the data. All right, we have each data point from our population, and that's what we are mapping out in our probability density function, any of our frequency distributions. We're going to talk about a special kind of distribution now, a sampling distribution. A sampling distribution is where we're going to look at a distribution of a particular statistic. It could be means, it could be standard deviations. Most of the time it's going to be means though. All right, the most common sampling distribution is the sampling distribution for sample means. And we're going to look at what would happen if we sampled X number of people, found their mean, wrote their mean down, put the people back in the population, and did the sampling process all again and again and again. So we keep calculating these means, and we look at what those sample means would look like in a distribution. So what's that distribution of means as opposed to individual scores? All right, this might not be making too much sense to you right now, but let's do some examples here. So suppose, if you would, that we have this tan colored box represents the population. All right, everybody that's in the population. Okay, to get a sampling distribution, we're going to randomly sample X number of people. Instead of saying X number of people, I should be saying N number of people, right? Because N refers to the number of subjects that are typically going to be in a psychology study. So we have N number of subjects. Maybe let's say that it's 10. All right, maybe our population is 100 people. We randomly select 10 individuals. We measure something of interest. Maybe it is their level of anxiety. Maybe it's their height. Maybe it's just, whatever attribute we're interested in. So we calculate the mean, and we're going to write that down in our notebook for later when we're mapping out this sampling distribution. So maybe we grab these individuals, okay, as represented by this circle here, okay? And then we throw those individuals back, and then we do this again. Maybe we randomly select 10 completely new individuals. And then we do this process again. Ooh, looks like we've grabbed 1 or 2 people that we've used previously. But if we're using random selection, this might happen where we just happen to grab the same person and might have them in multiple samples here. Okay, so instead of doing this 5 times, we're doing this infinite numbers of times, okay? And we keep writing down what those means are. And then we plot all of those means in a probability distribution, all right? When I was in graduate school, the guy that taught me quantitative methods in psychology was Jim Roberts. Okay? And Jim Roberts is a fellow South Carolinian. After I took his class, I was actually a TA for him for a year, and my wife actually worked with him, and she got her PhD underneath him. Great, great guy. But to demonstrate what sampling distributions were all out, he had a dance that he called the sampling shuffle. All right, and typically I'd get you to do this in class, but COVID and stuff, so we've got to do it virtually. So this is what we're going to do. There's a population out there, and we are going to reach out into the population and grab N numbers of subjects. All right, so then what we're going to do is we're going to calculate the mean of whatever. Maybe it's anxiety scores, maybe it's intelligence scores, whatever we're looking at. So then we're going to think about what the mean is. And then we're going to write it down in our notebook, okay? Write down what that mean is. And then we're going to throw those people back, okay? They're back in the population. And then we're going to do this process all over again, all right? So we go out, grab N numbers of people, calculate what the mean is, write it down, throw them back, and then do it again. And we'll do this for a while. Well, not just do it for a while. We'll do it infinite numbers of times to create what our sampling distribution is going to look like. Okay, so let's talk a little bit about what a sampling distribution is going to look like. All right, there are three qualities of the sampling distribution that we're going to examine. We're going to look at what is the mean of the sampling distribution, what is the standard deviation of the sampling distribution, and what is the shape of the sampling distribution. Okay, so we're doing all this calculating. We're going out, sampling X number of people, or N number of people, writing down what their means are, and coming up with this sampling distribution. What is the mean of this sampling distribution going to be? Well, property number one of sampling distributions, that the mean of the sampling distribution is going to equal the population mean. So the population mean just out there is for anxiety is a score 30. Well, the sampling distribution is going to have a mean of 30. Now, sometimes when we're doing that sampling, we're going to get a mean a little bit less than 30. Sometimes when we're doing that sampling, we're going to get a mean higher than 30, just because of random chance. But if we do this process infinite amount of times, the ultimate population mean of these sample means is going to be equal to the true population mean of what that score is. Okay. So the population mean of the sampling distribution, the population mean of all of these sample means, is equal to the population mean of the scores. So that's characteristic number one. All right. Characteristic number two. All right. What is the standard deviation of the sampling distribution? All right. This has a special name. It's called the standard error of the mean. That's a bit of a mouthful. So we typically abbreviate it. We either call it the standard error. So most of the time in class, I'm just going to call it the standard error. The way that we abbreviate it most of the time is SE for standard error. You'll sometimes see it abbreviated SEM. I don't really like this because SEM refers to something else in statistics. But if you see SEM, for the most part, it means standard error of the mean. All right. So what is the standard error of the mean? Is the standard deviation in that sampling distribution. All right. If we were to look at how all of the sample means vary from one another, all right, the standard deviation of those sample means would be the standard error of the mean. All right, the standard error of the mean is equal to the population standard deviation. All right, it's the standard deviation of the scores in the population. But it also is impacted by the number of subjects that we are sampling. All right. Is it 10? Is it 20? Is it 500? All right. So the standard error of the mean is composed of the natural variation in the scores, which is the population standard deviation, as well as the number of subjects that we are sampling. All right. If there's more variability in the population scores, the sample means are going to vary more. Okay. The higher the numerator is, the larger the expression is going to be, the larger the standard error is going to be. So the more natural variation, the more those sample means are going to vary, the greater the standard error. All right. Well, what happens as we increase the number of people that we're sampling? Instead of calculating sample means for 5 subjects, we're calculating sample means from 20 subjects. All right. Think about it logically beforehand. Do the sample means become more representative of what the true population mean is if we have more or fewer subjects? More, right? If we have 5 subjects that we're using and we're calculating the sample mean, sometimes we might just randomly have selected a bunch of people that are outliers, right? But the larger our sample size is, the more people we're studying, all right, the more people we're sampling, the more likely we are to get closer to what the true population mean is. Okay. So the greater the number of subjects that we're sampling, the smaller the standard error of the mean is going to be. And here's some examples of some sampling distributions of varying sample sizes. All right. So the data is the same. The natural variation is the same. The only thing that differs is the number of people that we sampled. All right. Notice that the variability is going down as n is increasing. All right. N equals 1, we've got a lot of variability. N equals 4, we have less variability. N equals 8, we have even less variability. In fact, the more subjects we sample, we're going to see that distribution pretty much shoot up like this. All right, because we are going to get very, very close to what the true population mean is, the more subjects that we have. All right, this is important to note. Okay, so we talked about what the mean of the sampling distribution is. We talked about the standard deviation of what the sampling distribution is. How about the shape of the sampling distribution? All right, this is where the central limit theorem comes into play. The central limit theorem is an idea in statistics that if we have a sample size of 30 or greater, it doesn't matter what the population distribution looks like. If it's skewed, if it's leptokurtic, if it's bimodal, doesn't matter. The sampling distribution is going to be normally distributed. All right, it doesn't matter if we've got a bimodal distribution. It doesn't matter if we've got some positive skew going on. It doesn't matter if we've got platykurtic distribution. It does not matter if we have 30 or more subjects that we're sampling. That sampling distribution is going to be normally distributed. All right, this is the central limit theorem. Now, you might be thinking to yourself, why should I care? Okay. Now, if it's the case that any data that we're looking at, if we sample 30 or more people, our sampling distribution is going to be normally distributed. We can use the normal distribution to answer questions about every single data set. That is really cool. All right. We're going to use the normal distribution to answer questions about any kind of data. It doesn't matter what that data initially looked like. It doesn't matter how fugly that distribution looks. All right. Our sampling distribution from that population distribution is going to be normally distributed, and we can use the normal distribution to answer our questions. Okay. Very, very cool. All right. So here's an example of what's going on. So let's say that our population distribution is skewed in some way. So we've got some positive skew going on. It's not awful, but you know, this is clearly not a normal distribution. All right. If we increase our sample size, okay, well, now we have a sampling distribution here at B, but our sampling distribution is 2. We only have 2 subjects. We're calculating the mean from those 2 subjects, and we're doing that dance that I showed you and coming up with the sampling distribution. It looks better. It looks more normal than the population distribution. All right, but it's still not normally distributed. Here we have the same data set, but we aren't doing, we're sampling 25 subjects as opposed to 2. This is a normal distribution. All right, this sampling distribution is normally distributed, and this is even before we have 30 subjects. All right, so whatever ugly distribution we have, with enough subjects, our sampling distribution is going to be normally distributed, and we can use the normal distribution with our statistics. We can use it as a basis for our inferential statistics later on. All right, so part 1 of the central limit theorem is that if we have 30 or more subjects, our sampling distribution is going to be normally distributed. That's part 1 of the central limit theorem. Part 2 is that if our population distribution is normally distributed, then our sampling distribution is going to be normally distributed. Okay, so maybe it's the case that we look at our population distribution, it's already normally distributed. Well, our sampling distribution is going to be normally distributed. All right, the shape of it is going to be normally distributed. So we don't have to have, in this instance, 30 or more subjects. We could have 20, we could have 5. The data is going to, the sampling distribution is going to be normally distributed. We only run into problems if we have fewer than 30 subjects and the data are not normally distributed. If that is the case, if we have fewer than 30 subjects and our population distribution is not normally distributed, we do not know what the sampling distribution is going to look like. Maybe it's normal, maybe it's not. But we can't bank on that. We can't bank on the traditional statistics that we are going to typically use in this class. All right. So let's ask ourselves a couple problems, okay, concerning sampling distributions. So here we have a researcher that's interested in a political issue. And it's like a hot button political issue, okay? And they have people rate their opinions on a 110-point Likert scale. You would never have this many points on the Likert scale, but for this graph to work, I had to finagle it that way, okay? The researcher is randomly sampling 36 students. They randomly sample 36 students, and then they write down the sample mean, and they toss those 36 students back. They randomly select another 36 students from the population and repeat this process an infinite amount of times. That's what sampling distributions are all about. The mean of the population of UNG students is 60. And the population standard deviation is 24. We are interested in three qualities of the sampling distribution. What is the mean of the sampling distribution? What is the mean of the sample means? That's the first thing. I just said it in two different ways. What is the standard deviation of the sample means, also known as the standard error of the mean? And three, what is the shape of the sampling distribution? We look at the population data, and how would we describe this data? Look at it. We describe this data as bimodal. People have either an extreme opinion about it, extreme opinion one way, or extreme opinion another way. Not very many people in the middle. The opposite of a normal distribution, if you will. So this distribution looks ugly. But if we calculate a sample mean from this, if we look at a sampling distribution, will the sampling distribution look just as ugly, or will it be normally distributed? Well, the central limit theorem states that if we've got 30 or more subjects, which we do, and if we do the sampling distribution with 36 students each single time, we're going to get a lovely normally distributed sampling distribution, okay? So according to the central limit theorem, we have more than 30 subjects. Doesn't matter what the population distribution looks like. We've got a normal distribution for our sampling distribution. Okay. What is the mean of the sample means? Well, the mean of the sample means the mean of the sampling distribution is always equal to the population mean. So we said it was 60 in the population. Our mean of the sampling distribution is going to be 60 as well. How about the standard deviation of the sampling distribution, also known as the standard error of the mean? Well, what we have to do is we have to get what the population standard deviation is, which is 24, and divide that by the square root of n. We have 36 students. Square root of 36 is 6. 24 over 6. The standard error of the mean is 4. Okay. Cool. Let's do one more problem. So a researcher is interested in studying depression on college campuses. She randomly samples 18 subjects and measures their depression on the Beck Depression Inventory. She writes down the mean and repeats this process an infinite amount of times. She's creating a sampling distribution. The shape of the population distribution appears below. Okay, that looks normally distributed to me. The population mean for Beck's Depression Inventory is 24, and the population variance is 36. So let's first talk about what the shape is. All right, I should have put the questions on this slide. Oh well. What's the shape of the distribution? Well, the population is normally distributed, so it doesn't matter that we only have 18 subjects, okay? Part 2 of the central limit theorem says that if our population distribution is normally distributed, then our sampling distribution is going to be normally distributed, okay? So that's what we've got here. What's the mean of the sampling distribution? Well, it's the same thing as the population mean, so it should be 24. Okay, the sampling distribution mean will be 24 as well. For the standard error of the mean, this is the population standard deviation over the square root of n. I gave you the population variance. So I want you to be mindful that sometimes you're going to need the standard deviation, and I'm going to give you the variance. Sometimes you're going to need the variance, I'm going to give you the standard deviation. Be mindful of that. So I'm going to have the square root of 36 in the numerator, which is going to be 6. That's the population standard deviation, over the square root of n, which is 18 here. All right. If I were to do this calculation, I'd get 1.414, which would be the standard error of the mean. All right. Sampling distributions might not be intuitive right now, and you might not understand why we're doing this, but if we're looking at inferential statistics, we care about, is there a true meaningful difference in the population between our experimental and our control condition? Well, we are sampling people. We're sampling people here, we're sampling people there. We need to know the natural amount of variability there are in the sample means. Okay, we need to know if the difference that we found between our experimental and our control condition is due to chance. And to examine that natural amount of variability that comes from sampling, we need to look at what the sampling distribution, what are the qualities of the sampling distributions. And that's where we're going to go forward in the next couple of weeks. So I hope you're excited about that, because I sure am. This is when we get into the meat and potatoes of this course. So super fun. Have a wonderful day, and I will talk with you guys later. Thank you. Bye-bye.